Hello everyone, this is a video for homework 10, and the first question we have to figure out is, from the definition and simple properties of the examples of the stochastic process, and we explain my personal extending. So let's find the first Poisson process. About Poisson process, we know that if x of t equals the number of denote the number of occurrence of an event in the interval 0 to t, and it has the first property is the number of points in an interval t1 to t2 is a Poisson random variable with parameter lambda times t, where t equals t2 minus t1. And the second property is if two intervals t1 and t2 and t3 and t4 are non-overlapping, then the two random variables n of t1, t2 and n of t3, t4 are independent. And the expected value or the mean of x of t is lambda of t. It equals lambda times t. And it's a linear function of t. Obviously, it's reasonable because when I'm waiting for a bus, and when waiting a line in the bus station, the longer I wait, the larger of the expected number of buses. Then the autocorrelation is lambda times the minimum of t1 and t2 plus lambda squared times t1 times t2. And the autocovariance is lambda times the minimum of t1 and t2. The third property is if x1 of t and x2 of t are two independent Poisson processes with parameter respectively with parameter lambda 1t and lambda 2t. If we defined another stochastic process y of t equals x1 of t plus x2 of t, then y of t is also a Poisson process with parameter lambda 1 plus lambda 1 plus lambda 2 times t. Then we define the d of t equals x1 of t minus x2 of t. Then the expected value of z of t is lambda 1 minus lambda t, and lambda 1t minus lambda 2t. And according to the linearity of expected value, we can easily get the answer. And about the variance of d of t, according to the definition, it equals the second moment of z of t minus the square of an expected value of t, and it equals expected value of x1 of t minus x2 of t squared minus expected value of x1 of t minus the square of the expected value of x1 of t minus x2 of t. And we explore this formula and we get it equals lambda 1 t plus lambda 2 t. And my personal understanding is as we place n random points in a line, say a timeline, the number of points in an interval t1 to t2 is a Poisson random variable with parameter lambda t2 minus t1. And the second Poisson increment. As we have known the Poisson process, if we define y of t equals x of t plus c minus x of t and over c. When c is fixed, let's find the property of y of t. And first, the probability of y of t equals n over c equals e to the minus lambda c times lambda c to the power n over n factorial. And the expected value of y of t equals expect value of x of t plus c minus x of t over c. It's 1 over c times lambda c equals lambda as a constant, and the autocorrelation of t1 and t2 equals 1 over c squared times lambda c squared, and equals lambda squared, and when t1 minus c is less than t2. And for t1 plus c is greater than t2, the autocorrelation equals lambda squared plus lambda squared over c minus lambda times tau over c squared, where tau equals t1 minus t2 minus t1. And we can say that the expected value of y of t is a constant, and the autocorrelation of ry of t1 and t2 is a function of tau, no matter t1 and tc is greater than or less than t2. So we can say that y of t is a wide-sense stationary process. And since Poisson increments is a wide-sense stationary process, we can say that Poisson process has stationary increments. It's like if we are waiting in a very, very long line, just the people waiting out of a store when Black Friday, so it's a very long line. So within every hour, the expected steps I can go forward are the same, no matter how long I have waited. And third one is normal process. The definition is a process x of t is called normal if the random variable x of t1, x of t2, x of tn are jointly normal for any n and any t1, t2, tn. The expected value of x of t is a function of t, and the autocovariance of t is sigma t squared. We can say that the first order density function x of t, f of x t, is a normal distribution with mean of eta of t and variance. Stationary variance is square root of c of t. And additionally, if normal process is wide-sense stationary, then we can say it's also strict-sense stationary. And if normal processes, the nth order characteristic of function of x of t is given by this formula. So if x of t, so if a stochastic process x of t is normal and WSS with mean eta of t and autocovariance c of tau, where tau equals t1 minus t2, then this formula is equals this, which is time invariance. So it's not only WSSS but also SSS. Thank you.